Okay, so describe the blind spot. Where is the location of the blind spot? Why can we not perceive vision when light is refracted from the lens to the blind spot within the eye? Anybody try that then with the blind spot vanishing, the dot in the book? Anybody try that? I know we tried it yesterday, but some of you said it didn't work. I don't know if you took it home with you on your iPad and tried it out. It should work. Should work. You go to any Hershey Bears games now? Oh, okay. They're always fun to go to. Every time I go, there's always a fight. It's awesome. They're affiliated with the Capitals, right? The Caps, yeah. Mr. up here today? Yeah. Try calling me, didn't answer. What did you say? Oh, I thought you said he was ignoring me. Could be doing that too.
Yeah, he was walking out.
Oh, was he? I thought hurricane season was over. Such a dumb part of the movie, but funny. I thought you said you saw it. All right, blind spot. What is it here? I know we talked about it yesterday, day before too, I think. What do we have here? What do we got? Noah, what do you got? Yeah, good job. Good job. So we talked about the anatomy of the eye and the parts, functions. And we all know that the blind spot is where the optic nerve enters through the eye, the back of the eye, the retina. And there are no photoreceptors located there. So that means you can't detect. You can't detect any type of visual light, obviously, where you can perceive vision. And that information won't be sent, and neural messaging won't be sent to the occipital lobe to be processed. So yesterday, I know, showed you guys with the book. Obviously, it didn't work out for you guys. Feel bad. Usually it does. Works for me anyway. And how when light is refracted, when it is reflected back to the retina onto the blind spot, we can't visualize it. We can't see it. We can't perceive it. All right. Okay. So terms for today. So I want to talk about color blindness today. I want to talk about the electromagnetic spectrum, amplitude, frequency, wavelength, and how it works with vision. I think I had opponent processing theory yesterday. I'm not sure. I did? Okay. All right. I didn't get to talk about it much, though, I don't think. All right, you guys ready? No? One more minute. One more minute. Yep, we're going to do that next, probably tomorrow. Why is that? Well, like it does apply to certain forms of light rays too. So with the electromagnetic spectrum, you're looking at gamma rays, depending on comparable to radio waves. There is a frequency, wavelength, and amplitude to that as well. All right, so what do we have? Electromagnetic spectrum. What do you got, Brady? Yeah, good job. So we'll talk about forms of wavelength, frequency, amplitude, and how it applies to really light rays, okay? And radio waves comparable all the way to UV light, to gamma and X-ray, and where it falls on the electromagnetic spectrum. As you move closer to gamma rays, you're going to have a higher frequency and a shorter wavelength. And much like you'll have a higher amplitude as well. And as you move further down the electromagnetic spectrum to the right side of it, you'll find radio waves, okay, microwaves even, and how these wavelengths are a lot longer, okay, which are shorter frequencies, or sorry, longer frequencies here. So we'll talk about that today and how there's only a small portion of the electromagnetic spectrum that we can actually visualize, that we can actually see. And some of these light rays, we can actually feel it with obviously UV light, okay, and infrared, okay. But some cases we can't even see these form of light rays. Okay, there's only a small portion, which we'll talk today about. All right, what about frequency? What do we have? Frequency. Kiara, what do you got? Okay, good. So this will also apply, like we were talking about, Raven, with auditory processing, okay, with sound, but also with vision. And with frequency, that is the amount of waves that are occurring in a given location, a given spot, okay? And when we're looking at the electromagnetic spectrum, depending where you're located, depending where you're looking at, again, on the far left with gamma, it's going to be a higher frequency. There's going to be more waves that occur at a given point, which we can't see, we can't visualize. But when you look at the very far right, it is going to be a lower frequency, okay, with shorter wavelengths, okay, some being as long as football fields. And obviously we can't see radio waves, but they occur at a given point. Amplitude, what do we have? What do we have for amplitude? Christian?
Amplitude is the measure of the magnitude of wave oscillation during the wave cycle.
Yeah, good job. So depending on the amplitude, obviously depending on the wavelength, depending on the frequency, the amplitude is just how high that wave is occurring, how high that is intensifying from the line of equilibrium, the line of equilibrium. And if it's a higher amplitude, that means it's going to be a higher pitch sound. Okay, same with vision. Okay, if it's a higher amplitude, if it's a higher wavelength, okay, a higher wave, then it's going to be a more intensified version of light, okay, which we'll talk about. Wavelength, what do we have? What do we got? Haley, what do you have for wavelength? Yeah, good job. So the peaks of the wave, and that will indicate frequency, okay, whether it's a low or high frequency. All right, so today, again, I want to talk about vision, electromagnetic spectrum, and just understanding wavelength, okay, and amplitude vision. So the visual cortex. So I talked a little bit about this yesterday. Okay, we're processing light rays. Okay, we're processing what we're perceiving as vision, color, motion, form, and depth. Okay, all at one point, all at one time. And it's amazing how we do it. We'll talk about it with binocular vision and how we're visualizing stimulus and our brain is perceiving it. It's all happening within milliseconds, really. And we're associating, we're understanding color, motion, form, and depth. I know I talked about it yesterday with my friend who's driving. Whenever I drive a car with him, he has, I think, a impaired depth perception. As we're getting closer to stop sign, it seems like he's just not understanding how to hit the brake and slow down before we get to that stop sign. It's like, oh, we're good, we're good. Oh, no, we're not. I'm going to brace myself because we're going to fly out into the road. And I think that just goes to show exactly how many people have different forms and understanding perception of color, motion, form, and depth. But the visual cortex located in the occipital lobe processes and perceives this information all at once, all of this, which is amazing to think about. It happens fairly quick. All right, so after images, I'm sure you've maybe encountered this before, but this is just a simulation, just goes to show what after images are. So stare at the eye of the red parrot while you slowly count to 20. Then immediately look at the one spot in the empty bird cage. The faint ghostly image of a blue-green bird should appear in the cage. So I'll give you guys a little bit of time to do that. So I always understood the more you blink, you'll be able to see that bluish bird in the bird cage. Anybody see it? Yeah, okay, yeah. So again, they call it ghost images, after images, because obviously it's nothing that we can perceive in the bird cage, but after staring at let's say a bright red or a bright green color for a long period of time, especially if they're associated together, our photoreceptors get tricked, right? We are, in many ways, actually blocking out these red stimulation, this red and green stimulation, and trying to perceive a different color, which is interesting to think about as your neural messaging is occurring with the bipolar cells, the ganglion cells, with the photoreceptors in your retina, in your fovea, which I think is pretty cool. So again, they're called ghostly images or after images. And again, that's called opponent processing theory. So I think I talked about this yesterday. So there are color combinations that are hard to visualize. Obviously, we get adjusted to it for some time. So our sensory adaptation occurs where we're actually visualizing something that actually isn't there. And that occurs a lot. Okay, that occurs a lot, especially if we're staring at the TV for a long period of time and maybe look away. We can still see some of these images after we turn our head. Or a lot of times when you're blinded by high beams, right? When you're driving a car, you're looking at high beams, and after some time, you still kind of visualize and see those high beams after a little bit of time because it's just so hard to adjust to, right? It's so hard to block that perception out of your mind, especially when there's so much stimulation all at once. Anybody encounter that? The high beams, yeah. Oh, can't stand them anymore with these LED lights. It's very difficult, I think, anyway, to see on the light, especially if they know if it's a high beam or not. What's that? The blue, yeah, yeah. They're blinding, right? It's like, how can you drive that? How is that legal? I'm always blinded by it anyway. So I oftentimes throw in my high beams, and then they throw on theirs. Oh, geez, okay, they weren't even on. It's amazing, actually. Any more of the Amish buggies have these LED lights on too. They're kind of blinding, I think, especially when they're projected back at you. But anyway, opponent processing theory is just how we're visualizing these different forms of stimulation perception. Okay, our rods and cones, especially our cones, obviously with the bright colors, we're visualizing something that maybe isn't there. So, colorless world, color blindness. Anybody know anybody that's colorblind? Yeah, who do we know? Really? What's that? Who? Oh, Hartman. Okay. Is he? Oh, I didn't know that.
Will is colorblind. Alex
Is there a commonality there? What's that? Yeah, they're all boys. Yep, good job. So this is a recessive trait that's actually passed down from the mother. Okay, it really only affects boys. Okay, males, which I think is interesting. My dad's colorblind, and there's a lot of times where we're watching TV and oh, those are cool uniforms. And do you like the brown on that? I'm like, brown? It's like a reddish, blue. Oh, I just perceived brown. Oh, geez, well, that's way off. Huh?
I just perceived brown.
Yeah, he didn't say perceive. I saw brown. I perceived brown. Oh, really, Dad? Cool. Yeah, but anyway, with color blindness, there's many different. There's 4 different types of red and blue. Okay, and red and green, and then there's 2 different types of blue, yellow color blind. And it's hard to associate with brown. Obviously, red and brown kind of go together with that when they're perceiving this type of vision, this type of color. And green as well, very difficult for people with color blindness to see. And I actually have a picture of flags and American flags, and it's kind of interesting to see exactly how these people see and visualize the colors of the flags. All right, so color blindness. All right, I do this simulation, this activity with my dad, and the one on the right is hard for him to see because he can't really see the red within that picture. So we all know on the far left what we have here, what number is it showing? 74, far right, 68. Okay. So it's very difficult for some of these people to see and perceive what number actually it is. It just goes to show, depending on their color blindness, how it might affect them. Here's another example. So these flags, okay, this is kind of how these people see and perceive the colors. So one is by most people with form of color blindness, obviously, or sorry, that is number one is what we visualize a flag as. Number two, red blind. Okay, so this is red blind person, color blindness for number two, which is right over here, guys. You can see that kind of looks like the red stripes on the flag are green. Couldn't imagine seeing that. Three, by green blind person. Okay, so three is here on the far left. That's a little bit darker blue, I guess, but for the most part, you can kind of see it's American flag, no problem. Four, violet blind person. So again, you can kind of see it's an American flag. Maybe the blue actually looks more like a black, kind of. And then five is total color blindness. Okay, so as you can see, it's gray. I couldn't imagine seeing everything black and white. It'd be terrible. It'd be terrible. All right, so electromagnetic spectrum. I want to talk about this. So again, wavelengths, okay, and how this occurs, frequencies, amplitude, even with vision, okay. And at the far right, you'll see more of radio waves. And radio waves have a longer wavelength. Like I mentioned, they're more like the length of a football field. So when we're visualizing it, it's pretty far out. Okay. The wavelength is interpreted again by the peaks of the wave. And the amplitude is just how high the amplitude. I'm just going to put an A here. I'm going to put wavelength up here. And the frequency, obviously, is how many waves occur at a certain given point. So if there's multiple waves, it's going to mean that there's going to be a higher frequency. A lower frequency means that there's going to be really not many waves occurring in a certain given point. So at the far right, with radio waves, moving to radar, infrared, you're going to have a longer wavelength. So as you're getting closer to what we can actually visualize, which I think is interesting, of the electromagnetic spectrum, you only can see just a small portion. And we only can see only a little bit of the electromagnetic spectrum. We can feel infrared rays. We can feel ultraviolet rays, obviously from the sun. Okay, we get sunburn. Right? You can feel those, but you can't see them. So again, as you're getting closer, these wavelengths are going to become shorter and shorter to a point where they're going to be almost really touching each other. Okay, the frequency is going to be a lot higher. Okay, your amplitude is going to be a lot higher as well. So as you're moving further left on the electromagnetic spectrum with gamma rays, X-rays, okay, the frequencies are going to be a lot higher. The wavelengths are going to be a lot shorter. And the amplitude is going to be much higher as well, as it's going to be a more intensified, increased frequency, okay, increased light ray, gamma radiation, the Hulk, right? So here's an example, obviously. The short wavelength means higher frequency. Okay, that just means it's closer together. The wavelengths are closer. So there's going to be a higher frequency. It's going to be a more intensified version of light. So gamma rays, X-rays. Obviously, with X-rays, we can visualize our bones and see any type of problem we might have, a breakage in a bone. And that's being shot through the body. Okay, as we're getting closer to the center where we can see, the wavelengths are going to become a little bit further apart. The frequency is going to be a lot lower. So here again, long wavelength, low frequency. That you'll find on the far right with radio waves, okay, and microwaves even. At the very top, a higher frequency, shorter wavelength. You're going to see that more at gamma rays, okay, X-rays at the far left. And we're kind of in the middle, that only small section you can actually visualize. Again, amplitude is just how high that wavelength is comparable to the line of equilibrium in the middle. And this might be more of a bright color. Okay, this is going to be a brighter color, and lower sound, small amplitude, dull color, soft sounds. So when you compare that to auditory processing more tomorrow and the anatomy of the ear, that's kind of what we're getting into. Is everybody good with electromagnetic spectrum? So again, we only can see a small portion. At the far right, where we see the radio waves, microwaves, you're going to see a larger wavelength, longer wavelength, okay, and a shorter frequency, as there's less waves occurring in a given point. Same thing at the far left, obviously that's going to be a higher frequency, lower wavelength as it's being intensified, right? So you'll see gamma rays, X-rays at the far left of the electromagnetic spectrum. All right, finally, visual pathway. Last thing I want to talk about is how we perceive, okay, certain perceive vision and visualize certain objects or understand what we're seeing. So again, when we're visualizing something, this is actually being processed on the opposite side of our brain in the occipital lobe. And we're actually flipping the image upside down. So as we're visualizing anything, it's actually upside down of what we're visualizing. So in our brain, we're processing it right side up so we can understand and actually see what we're visualizing so we can react to it, which I think is interesting. So you remember when we talked about the Corpus Callosum, when that was sliced with that man with epilepsy? Yeah, okay. And he had a problem associating what he was visualizing. That goes to show exactly how that works. When that corpus callosum was sliced, there was no communication between the two hemispheres of the brain. So he really couldn't pronounce and understand what he was seeing, but he could draw it out. And whatever he was visualizing on the left side, okay, he couldn't speak about it. He couldn't discuss because Broca's area or Wernicke's area on the left side of the brain. He could draw it out, but he can't express what he was seeing. And obviously that was the image on the left side. On the right side, he couldn't draw it whatsoever, but he could speak about it. He could discuss what he was visualizing, what he was seeing, which I think is interesting. So again, flipping that image upside down and is actually alternating to the other hemisphere of the brain. Okay, and your brain is perceiving this information and processing it right side up. We talked about it with color, form, depth, you name it, all at one time, which is amazing to think about. All right, is there any questions on vision here? We're just finishing that up. We good with frequency, good with wavelength, amplitude. We good with color blindness. Okay, how photoreceptors might be altered, obviously, depending on stimulation. Component processing theory. Okay, that's all I have for today. Remember to understand that with the anatomy of the eye. Now that all makes sense.